So my talk is the last one of this long day, and just before your dinner, so I will try to be quick and clear. And I need to apologize in advance because, our section really have very nice talks and discussions, so I cannot really make a very conclusive coverage as what just Mike did. So I strongly recommend you, if you are interested, to also go through the slides, and you will find lots of interesting ideas and new results. Okay. So I start with some general introduction. So that everyone here, I think we share the same the same point of view that the standard model is not the end of the story. We have many, many defects in the standard model. And interestingly enough, that all those things they seem to be associated with the Higgs boson. So we really want a precise Higgs factory that can tell us the nature of this boson, and we really want to see through this boson. Okay. So that slide was taken directly from Fonko, and basically along this line of thought, many Higgs factories was proposed, and some the linear ones was even proposed before the Higgs discovery, and there are also these two new circular ones. So if we use the CEPC parameters as a benchmark, then actually this can be benchmarked as it will produce 1 million Higgs boson and 10 to the 8 W boson and 10 to the 11 or 10 to the 12 Z bosons if in the FCC cases. And the FCC also will be a very, very powerful top factory, and then can produce 1 million top of the order of 1 million tops. Okay. So the beautiful of the Higgs measurement at the E plus E minus factory is twofold. The first is that the E plus E minus machine is extremely clean. So then, in principle, the inclusive cross-section is just, 2 to 3 orders of magnitude than your Higgs signal. So that means you really have very, very clean sample. And on top of that, you have very clear signature of all these events. So you can easily separate your signals from your events. And the second thing is that, especially at the circular colliders at the lower center of mass energy, actually most of the Higgs boson is generated from the ZH process. So then you will have, you can do the absolute measurement through the recall mass method. Okay. So yeah, actually in this way, then the measurement at the E plus E minus and at the PP is highly complementary. So on the detector side, actually, both CEPC and FCC EE, then we have two conceptual detectors. The CEPC, we use PFA-based design as a baseline and the idea detector as alternative. And for the FCC EE, there is also one PFA-oriented design and the idea detector. So currently, with lots of efforts and the software and the reconstruction, we can basically do a decent job of how to extract all the information from the collisions from the detector side. And basically, we aim at reconstruct every kind of the key physics object. So currently, what we can do is that we can basically have a pretty good coverage on the photon reconstruction, leptons, kaons, jet Smith energy missing momentums, and jet flavor targets. And for the jet energy and jet momentums, basically we can separate the WZ Higgs as this is highly appreciated. So once you can do your object at this level of accuracy, then certainly you can easily find all the Higgs signatures. So then this is the Higgs signals with the different decay modes as the Higgs to BB, CC, GG, and WW and ZZ. For WW and ZZ, their cascade was further classified according to how many neutrinos, according to the neutrino numbers that will be generated. So what is the extremely characteristic is about this Higgs to ZZ inclusive mass distribution. So you will have totally invisible one, since you have 4% of the Higgs to ZZ then goes into invisible. And you also have this fully visible and the semi-visible conjugation pairs. Okay. So this is basically how well we can currently do with the current detector design and the reconstruction. So basically, if you have both the accelerator and you have the detector, and then this leads to actually very, very nice measurement. And this had been tested on different kinds of geometry set, different kinds of reconstructions, and it's all confirmed that for the Higgs measurement, we will be reached at percentage or even sub-percentage level accuracy for the signal strength measurement, let's say. And this is for this work, then we have been confirmed that for the Higgs kappa measurement for the for the kappa measurement and the coupling measurement, then actually we will do 1 order of magnitude better than what can be done at the high luminosity LHC. And currently, we are currently working on the CEPC Higgs white paper, and we will soon have it released. So, so this is the part about the Higgs, and then this is also the part about the electroweak measurement. So basically, for both CEPC and the FCCEE, that will be a tremendous, Z factory and also W factory. So the productivity will be 4 to 5 orders of magnitude compared to the lab experiment, and this certainly means a huge, measurement accuracies for this electroweak observables. So the electroweak observation measurement can actually be quite well characterized by the W mass measurement, which is very sensitive to the new physics. And so now lots of studies have been done, for example, as the W mass scan to searching for the optimized point for the W mass scan in terms of the statistical uncertainty. But meanwhile, we are not only about the statistical uncertainty, what is more important is about the systematical control. So then the core element of the systematical control for this benchmark, they had been, decouplerized and to be quantified. So for instance, if you want really to have a very good W mass measurement, you need to calibrate. The key element is to calibrate your beam very, very precisely. Meanwhile, you also need to calibrate the efficiency, the acceptance, and the luminosity, et cetera, et cetera. So then, actually, in the relatively ideal case, I would say that the future electron-positron colliders certainly provided a very, very precise measurement for all the electroweak measurement. And this can be compared in those benchmark plots where you say that if the value is still centralized as nowadays value, then clearly with these new facilities, we will see very clear deviations from the standard model. And that is also about the triplet gauge boson couplings, and this we can certainly do 2 orders of magnitude, or 1 to 2 orders of magnitude better than the current precision, and with respect to the LHC limit. So which is actually, in other words, approaching to the statistical limit. So that's actually one of the very, very important conclusions of this talk, of Paolo's talk. So for the electroweak measurement at the FCC and CEPC, so no a priori wall was identified to say that, okay, you are really saturated, your accuracy is really saturated at some statistic. So in other words, I think that is to say the statistic is always welcome. And then the key observables can be basically measured to an accuracy of at least 1 order or even 2 orders of magnitude better than the lab. And meanwhile, that our CEPC colleagues confirmed that this conclusion is basically, confirmed from the CEPC studies. And the systematic studies is certainly the core of this game, and part of the requirement on the detectors and the beams and the other components had already been quantified, so which I regard this as really a nice progress. So then I would just switch to the last talk of our section, which is given by Alain. So Alain talked about the control of the most important systematics. The systematics arrives from the beam. So basically then we have a general discussion on the luminosity monitoring, on if we need the longitudinal beam polarization or not, how to maintain the transverse beam polarization, and how to calibrate the beam energy and beam profiles. So actually, just as the statistics here is huge, so it makes very, very demanding for the beam energy measurement. And then this is the benchmark productivities of the bosons at the FCCEE and the corresponding goals for the center of mass energy measurement for the FCCEE. And this exploration was actually, pretty deep and a full spectrum, I would say, because it covered all the key electroweak observations, and then it had been decoupled into the dedicated quantified requirement and had been, identified for the most crucial subdetector system and the component, and also about the theoretical uncertainty limits here. And meanwhile, lots of new ideas had also been proposed and mentioned in Alain's presentation. So for instance, because at the z-pole operation, you are going to have a lot of E plus E minus 2 mu mu. And then using this in-institute calibration, for every 5 minutes of the data taking, you can have already a pretty decent control of the beam energy. Okay. And then we also have a talk on the top physics in the scope of the linear collider, but the circular collider itself can also do, as the FCCEE, can also do the very nice top physics. So for the top physics, then lots of effort had been put in for the linear collider studies, and many benchmark studies was carried on at the full simulation and full reconstruction level. So where you see immediately lots of very, very important systematics, very important effects need to be modeled. And so this is a very sophisticated analysis with respect to the measurement of the polar angle distribution and the forward-backward of the top. And now this was matched pretty well in between the simulation and in between after the correction of the mitigations. And for the tops, actually, there are many, many observables, many key measurements. So you can measure the top mass, top width, and the flavor changing neutron currency, and the top quark electroweak measurement, which is quite characteristic to clarify different new physics models. And of course, if you continuing update your center of mass energy as in the linear collider, you can do the top and Higgs recover couplings precisely. Okay. So the top mass study had been basically discussed under the threshold scan, which is a very, very precise method. And the people believe that this method leads to an accuracy better than 50 MeV. And actually, the Paul masses, the statistical errors and the decompositions of the systematics can always be much smaller than that. But from the theoretical point of view, people still need to understand, to have better interpretations of what is actually measured. Okay? So that, in other words, that from the experimental side, then we really makes pressures to the theoretical part. And also the top couplings, the top electroweak couplings, they can be determined. This is also the analysis, I believe, at full simulation level. And this is discussed under the effective Lagrangian framework, and all the couplings can be measured to a very high precision at the linear collider with respect to the LHC result and the existing result. Meanwhile, there's also a discussion dedicated paper from Jeannot, from Patrick, and discussing about the measurement at the circular colliders. Okay. So basically, the main conclusion from this top presentation is that the linear collider top physics program is highly complementary to what can be done, what can be carried at the LHC and the high velocity LHC. And the typical mass and the recover couplings and the accuracies was given here. So of course, there is another talk covering the beyond standard model. So the beyond standard model, the new physics research was discussed with respect to the huge productivity in the Higgs factory, the Z factory, and also at the flavor factory. The first thing is that so these factories, they can be used to have a very sensitive probe for the exotic Higgs and Z decay mod search. And meanwhile, it's not only that, we can also use them to searching for the new particles, or searching for the long missing particles as the WIMP, as the stellar neutrinos, and searching for the dark photons, et cetera, et cetera. Basically, the productivity and the cleanness ensures the high sensitivity to all this measurement. So then I rush into my summary. So basically, I think certainly that at the E plus E minus, we have great opportunities. And on top of that, I see a lot of substantial efforts and progresses for the understanding of the systematics and for the complete reconstruction and the designs of the detectors. Thank you.
Okay, we have time for questions.
You showed in one slide that for CEPC an uncertainty on the number of Z bosons produced between 10 to the 9 and 10 to the 11.
No, it should be 10 to the 10 to 10 to the 11. I think 10 to the 9 is corresponding to the pre-CDR assumption, which is actually.
Ah, okay. No, I was surprised by why go so low. I mean, because in the end, your uncertainty at the moment is just this factor, roughly factor of 2 due to the magnetic
with
field.
Respect to the magnetic field, yes.
I don't expect to orders of magnitude.
Yeah,
okay.
yeah. So actually, the global productivity, if you just compare the CEPC and the FCCEE, then the Z we will have 50 times less. but for the Higgs, for the Higgs and Z, they will be basically at the same order.
Other questions? Okay, I think so. Well, why not?
Nobody wants to eat, do they? Sorry, you brought up the question about longitudinal polarization, and I thought you were going to answer it, but if you did, I missed the answer.
Yes. The polarization, the longitudinal polarization, well, according to Alain, but I think that's the consensus of the community, is that the longitudinal polarization is very nice, but at the circular collider cases, it's very expensive in terms of the, you need probably to sacrifice too much luminosity just for the polarization, and at the end, it doesn't necessarily lead to the better result and better efficiency. This was mentioned explicitly in Alain's talk, actually.
Okay. Charlie? Okay, well, let's thank the speaker again.